So let's take a look here. We're going to start to read through our question. So it says that we have these Roma tomato plants that cost $2 each, meaning they cost $2 to go buy them. And they are guaranteed to yield 8 pounds of tomatoes per plant. Okay, then we have another type of plant. It's a cherry tomato plant. Those ones cost $3 to buy, and they are guaranteed to yield 10 pounds of tomatoes per plant. Now, it says here you want to spend no more than $42 when you go and buy these plants for at most 15 tomato plants. So we can only have 15 plants altogether. How many of these plants should we buy to maximize the pounds of tomatoes we will get? So this reminds us of what we saw Tuesday. It's linear programming because it involves finding a maximum value. In this case, we're wanting to maximize the amount of pounds. All right, so let's start here with assigning our variable. And I want you to put a box around this phrase right here where it says how many of each plant. So that clue right there is going to help us to know how we should assign our variables. So we want our variables to represent the two different types of plants. You can always use X and Y as long as you define out what they're supposed to represent. I'm going to use R to represent the number of Roma tomato plants. So I can see here in the problem, that was the first type of plant it told me. And then I'm going to use C to represent the number of cherry tomato plants. That was the second type of plant that we had. All right, for our constraints, we are looking for things that we are limited by or that we are restricted by. So I want you to take a moment here, and I want you to talk with your table and tell each other, do you notice anything in the problem, any sort of wording about some limitations, some constraints that we would have? You don't have to write it out mathematically yet, but just using regular words, what are words in the problem that might be one of our constraints? All right, so we can spend no more than $42. And so let's take a look back up here at the problem. The Roma tomato plants cost $2 each. So I'm going to underline those pieces with the same squiggle because that is going to go together with the amount of money that we're able to spend. And then let's also squiggle here under the cherry tomato plants cost $3 each. Okay, so those pieces all together need to go into an inequality statement, and I want you to try writing this one. So on your paper, I want you to try to write out the inequality that matches the constraint that we can spend no more than $42. Try that. All right, so nice job here, everyone. Okay, so we have $2 multiplied by the number of Roma plants plus $3 multiplied by the number of cherry plants. All together has to be less than or equal to $42. So if we think about the wording, we're not allowed to spend any more than $42. We could spend exactly $42, or we could spend anything less than that. We just couldn't spend like $43. So it has to be less than or equal to. Now, another strategy, another thing that you can do here, like when you have your money constraint, is you could put a little dollar sign here next to all of the pieces just to double check and see, okay, all of the pieces that have to do with this dollar amount, I'm putting those together in the same inequality. Okay, so looking back at the problem, is there anything else that we're limited by? Do we have any other restrictions here?
Yes.
What else does it say?
Most 15 tomato plants.
Beautiful. Yeah, we don't actually have like unlimited space. Like we couldn't have 1,000 plants. We don't have room for them all. We only have space to plant 15 of them. Okay, so we're going to use a different symbol for this information. At most 15 tomato plants all together. Now, we actually don't really have anything else to circle necessarily that's going to lead up to this, but we just have to think about, okay, well, the number of Roma plants plus the number of cherry plants, so R plus C, the total number of plants, is at most 15, so we have another less than or equal to. Because we could fit 15, we could also fit 14, we could have 13, we just couldn't have like 16, because we don't actually have the space for that, so it's another less than or equal to symbol. Notice that, like, we would not want to put the 15, for example, here. That 15 is not representing the dollar amount like these ones are. We have kind of the same information that goes together. These are actually the only two direct constraints that are given to us in the problem. There's two more implied constraints that I want you to add in. And that is just that we cannot have a negative number of plants. That just wouldn't make sense. So if we're not given a lower bound, we're always going to add in that our variables have to be greater than or equal to 0. So the number of Roma plants has to be greater than or equal to 0. The number of cherry plants also has to be greater than or equal to 0. Now what that is actually doing is it's keeping our graph in the first quadrant, because that's where all of the numbers are positive numbers in here, which is how we would set up our graph anyway. If we didn't have those two implied constraints, we would actually be technically working with a graph that was in all 4 quadrants, going into some of the negative numbers, but we can't have like a negative number of objects. All right, so those are all of our constraints. Okay, let's take a look here at the objective function, and I want you to do some thinking and talking here again with your table group. If I have the first variable that's listed in the problem represented on the x-axis, you don't have to do it that way. That's just how I think about doing this. And if you want to try to stay more consistent together with how it's being presented here, that's typically what I do. So I would have the number of Roma tomatoes be on the x-axis, so that's going to be like the r-axis. And then the second variable that's listed, I'm going to go ahead and put that one on the y-axis. So here we have like the number of cherries. And I used the wrong words here, so it's not tomatoes, it's the number of plants. The number of Roma plants, that's R, and then the number of cherry plants would be C. Okay, another way that we can write this that would actually be simpler would be just to use R and C. Okay, so let's take a look at our constraints. So looking at the first one, we're going to think of this for a moment as being 2R plus 3C equals 42. So because the variables are together on the same side, I would think about the intercept method. So I'm going to think about finding the C-intercept first. So I'm going to plug in R for 0, or I can just cover up the R. So we're thinking of this as being 3C equals 42. Well, if you divide both sides by 3, 42 divided by 3 is 14. So on the C-axis here, I'm going to count up 1, 2, 3, 4, until I get to 14. Okay, so I'm going to label that as a 14 off to the side and also plot a point. Okay, now I'm going to move this over to get the R-intercept. So that's going to be when C equals 0. So here we have 2R equals 42. Well, here, if we divide both sides by 2, we get the R-intercept to be 21. Now, this little grid size that we have here goes out to 20. So this little marker line right here is 20. And so I'm just going to make one more position equal distance as the other sizes that I saw. That's going to be 21. And we'll go ahead and label that here. That's going to be our R-intercept. All right, I want to give you a couple of tools here for connecting our points. Option number 1 is to use a straight edge or a ruler to ensure that you are crossing through the exact position you're supposed to cross through. If you don't have a ruler, I would absolutely not try to free draw this by hand, just because I think it might be, our line might get a little bit off. So here are a few other options. If you didn't have a ruler, we could calculate the slope here from one point to the next, scale down the slope to a smaller fraction, use that smaller fraction to figure out points that are in between. So remember that slope is the rise over the run. So this is up 14, and then we're going over 21 to the left. So if you actually think about starting here at the bottom and getting our slope, it would be like going up 14 spaces and then over 21. Well, slope, we know that is rise over run. Off to the side here, I'm going to say here that our slope is 14 over 21. Well, if we divide the top and bottom by 7, that's going to actually scale this fraction down to be a lot smaller. It is the same thing as a slope of 2/3. It's actually negative 2/3 because it's like a decreasing line. So here's what that would look like. If we start down here at the bottom and go up 2 spaces, over 3 to the left, up 2, over 3, and continue that pattern all the way to the other side, we should end up at that ending point. Up 2 over 3, perfect, up 2 over 3. Okay, now that you have more points that are plotted on there, now it would be okay to go ahead and draw your line through those points, even if you don't have a perfect ruler with you. All right, now I want to give you another option that you can do to figure out the slope here. Another thing that we can do is we can take the equation that was used to make that diagonal line. Now remember that that came from our constraints. So if we look back over here at our constraints, I'm going to uncover what we covered. It was 2r plus 3c equals 42. So another way would be to go ahead and rewrite that as an equation off to the side. 2r plus 3c equals 42. Now, which one of these variables would be like the y variable? Which one did we put on our y-axis? We put c in there. Yes, so we have c on the r-axis. Well, that's kind of like our y value. So remember that back in chapter 2, if we could get our equation written in terms of y equals something, we could get slope-intercept form and we could figure out the slope. Well, we could actually do that here by solving for c, because that's kind of like representing y, and that would tell us what our slope was. So to get the c variable by itself, we could subtract 2r from both sides. So here we have that 3c is the same thing as negative 2r plus 42. Then when we divide everything by 3, we're going to see the same result here, that our slope is negative 2/3. So this is the piece that we're paying attention to. Like, what does that fraction end up being in front of our other variable? And that would be another way to use our slope to get from one point to the next. All right, so either way, however we do this, it's going to be really valuable to at some point find the slope so that we can get these other points here along the way. All right, now it is an inequality, not just a line, so we do need to figure out where the shading is going to be. Would we be allowed to use 0, 0 for a test point here? Yes. Yeah, 0, 0 is very far from the line, so we can definitely use that. So if we were to plug in 0 for r and also plug in 0 for c, it looks like here we end up getting that 0 is less than or equal to 42. Is that true or is that false? That's true. Okay, so let's go ahead and shade toward 0, 0 because it was true. We'll just go ahead and do these little arrows pointing toward that direction. Okay, the second line that we have to graph here for our constraints, this one is actually going to be a little bit easier. R plus C, we're going to think of it as being equal to 15. Well, if we get the C-intercept is 15. Always plot the point and put a label off to the side for the number. And then look at this, the R-intercept, when you put in 0 for C, the R-intercept is also 15. And we count backwards here, 19, 18, 17, 16. Okay, so 15 is going to be right here. And what's beautiful about this, when it's the same number for both of your intercepts, your slope is always -1. If you think about it as going up 15 over 15, that simplifies to 1, but we have a negative slope again. We can go ahead and count like up one space over one space to get these little points in between. And when we continue that, it should end up at the other intercept up there on the C-axis. We'll go ahead and connect those points there. Now let's think about the shading this time. If we plug in 0 for each one, okay, hold on a second. I got a little bit messed up. All right, if we plug in 0 for each one here, we get 0 is less than or equal to 15. What will we say about that one? Is that true or is that false? That one's true again. All right, so we're going to shade towards 0, 0. So it's going to be down below this one. Okay, for the last two, let's talk about these ones down here at the bottom. If R is something that's greater than or equal to 0, that means that we have to shade to the right of this line, because that's where the R values are bigger than 0. And then for the very last one, if C also has to be greater than or equal to 0, we're going to be shading up from the bottom. That's where the C values are greater than 0. So that, again, is just keeping it in the first quadrant. No negatives. Okay, so now we are going to identify where all the shading overlaps. And we want to be really careful here. Notice that it's below both lines, but they cross over. So at this first part here is below the blue line. Then the lines intersect. Now it's below the red line. So we're just going to kind of do our best to shade in. This is called the feasible region. It has all of the combinations that make all of the constraints true. One of these possibilities will be the one that gives us the maximum number of paths. Okay, so now it's time to go ahead and identify the vertex points, the corners of the feasible region. It's going to be one of those that gives us our maximum. And so above vertex, I'm going to go ahead and write R, comma, C, just kind of like X, comma, Y. So we have R on the X-axis, we have C on the Y-axis. And then if we go back here into our graph, I'm going to try to make these really bold so they stand out. There's 4 vertex points that we're looking at. I'm going to put those here in green. This one right here where the 2 lines intersect, notice how that's a vertex point. And then we have that other piece down there at the bottom. Only the points that are listed here in green are the ones that we're going to put into our chart. And it doesn't matter the order that you list them out. I usually start down here at the bottom with 0, 0. We're still going to put that one in our chart, even though it seems a little strange to have 0 plants. If we put our objective function right here on top of our table, 8 times R plus 10 times C, well, if we have 0 plants, we're going to end up with 0 pounds. All right, let's go ahead and look at our next vertex point. So that's going to be the next one right here, 0, comma, 14. So 0 Roma tomato plants, but 14 cherry plants. And when we plug this one into our pounds equation, we notice that we end up getting 140 pounds. So certainly quite a bit more than 0. but we still need to test the other two combinations. Now, the next vertex is going to be very easy for us to get, even though it's in the middle part of our graph. We were so careful in drawing our lines in, and we were very careful to use our slope to get exact points. We can look straight down here and see, okay, that's 3 Roma plants. And then over here, on this side, that's 12 cherry plants. So we're just getting the coordinates of the point by looking at where it is on the graph. So that's 3, 12, but I'm going to actually transfer it over here. So if it was 3 Roma plants, we have 8 times 3, and 12 cherry plants, that's going to be 10 times 12. All of that together is a little bit better. That gives us 144 total pounds. So right now, that seems to be the best option, but we still have one more vertex point to check, and that's this point down here representing that all 15 plants are Roma plants, and that we have 0 of the cherry tomato plants. So 15, 0 is going to be our last vertex. So we're going to end up doing 8 times 15 plus 10 times 0. Well, 8 times 15 is 120. So it wasn't as good as the other option that we had right before that. Before we list out our final answer here, I just want to say one more thing about getting the vertex points. Sometimes students add extra vertex points that they don't need. So for example, on the graph, they would also include this one, or maybe also include this one here on the top. However, notice how that's not a vertex point of the shaded region. It was a point that we needed to figure out where the line was going to be, but that's not actually going to go on our chart. So we need to know that we're just ignoring those other points. We're not just listing out every single point that we see. So I'm going to put some purple X's through those because we do not need to include them in our list of combinations. Okay, so at the very end here, we are always going to put our answer back in words. Remember the how many question at the very beginning was how many of each type of plant should we buy. So I'm going to circle the best combination in the chart, but I'm also going to write it out in words. So it looks like it was 3 Roma plants, 12 cherry tomato plants, and then we're also going to say that the maximum number of pounds was equal to 144 pounds.